G'day. Today I want to talk about indices and word problems. I mean, we're going to use indices to solve those word problems. Question number 1 is a rhyme from the 18th century about going to St Ives in England, and here's a little map to show you where St Ives is in southwest England. The rhyme goes like this.
As I was going to St Ives, I met a man with 7 wives. Each wife had 7 sacks, each sack had 7 cats. Each cat had 7 kits. Kits, cats, sacks and wives. How many were going to St Ives?
Now the trouble with this problem is that it's not clear who was going which way. But in the 18th century, I understand that to meet someone on the road usually meant meeting them coming the other way. But there are several scenarios, and I'd like to look at them now on the whiteboard. Let me call this situation A. The man in the party is coming this way, maybe from St Ives, and the narrator is going to St Ives, and they meet on the road. Well, in that case, the answer would be 1. Not very interesting from the maths point of view. Here I have situation B, where there's a crossroads, and the man with the party is coming from left to right, and the narrator is, of course, going to St Ives, and they meet on the road. And in this situation, the answer is again 1. And here we have situation C, where 2 roads converge to form 1. And the narrator is coming up one arm this way to St Ives, and the man with his party are also going to St Ives. We could also have a situation where the man and his party, because of its size, were going along the road quite slowly, and the narrator, going along the same road, caught up to them on the way to St Ives. In this situation, the answer is not 1, but we have to count the narrator and the party. And if we go back to the worksheet, I'll show you how to do this. Back to the rhyme. If you'd like to hear it once more, here it is.
As I was going to St Ives, I met a man with 7 wives. Each wife had 7 sacks, each sack had 7 cats. Each cat had 7 kits. Kits, cats, sacks and wives. How many were going to St Ives?
How many were going to St Ives? Well, let's count them. As I was going to St Ives, 1. I met a man with 7 wives, plus 1 plus 7. Each wife had 7 sacks, so that would be plus 7 by 7. Each sack had 7 cats, plus 7 by 7 by 7. Each cat had 7 kits, would be plus 7 by 7 by 7 by 7. So now we must add all of these. Kits, cats, sacks and wives, how many were going to St Ives? So it's 1 plus 7 plus 7 by 7 is 7 squared plus 7 by 7 cubed plus 7 to the 4th power. Now if I just expand those powers, I get 1 plus 7 plus 49 plus 343 plus 2,401. And the answer to that is 2,802. We're going to St Ives, given that this was the situation. Can you see that seeing things in terms of indices makes it easier to handle? All right, let's do question 2. If you have a ring which you bought this year for $70 and it doubles in value every year, how much will it be worth after 20 years? Well, this year it's worth $70. Next year it will be $70 by 2. After 2 years it will be $70 by 2 by 2. After 3 years, $70 by 2 by 2 by 2. And after 4 years, $70 by 2 by 2 by 2 by 2. Now, isn't it obvious here that what we have here is the powers of 2. 2 squared, 2 cubed, 2 to the 4th power. And the pattern is, it's the original price of the item multiplied by the power of 2 to the number of years. So after 20 years, by 2 to the 20th power, which is 73,400,320. Question 3. Say you are having a long party. You invite 2 friends. The next day, the party is still going, so you invite 2 more, and your 2 friends also each invite 2 of their friends. On day 3, no one leaves, and you invite 2 more friends. Your friends each invite 2 more, and their friends from the previous day each invite 2 more of their friends. If this pattern continues, how many will there be at the party after 1 week, after 2 weeks? Well, if we have a table, we can pretty well work out what's going on. So on day 1, there is you, and you invite 2 friends. On day 2, you continue at the party, and you invite 2 more friends. Your friends continue at the party, and they invite 2 more of their friends. Each of them invites 2 more. So after day 1 we have 3 at the party, and after day 2 we have 9. Now, on day 3 you continue at the party, and so do each of these guys. They're all continuing. No one is leaving. But what happens is each of these people invite 2 more. You do. Your friends from day 2 do. Their friends do. And so on. And how many have we got? We've got 3 9s there. 27. Well, it should be obvious. The pattern is the powers of 3. After 1 week, the answer will be 3 to the 7th power. which is 2,187 people. After 2 weeks, with this sort of party, there will be 4,782,969 people. And that would be a big party. Let's move on to question 4. In a month of 30 days, a man is given $1 on day 1, and the amount doubles every day. $2 on day 2, 4 on day 3, 8 on day 4, and so on till the end of the month. How much will he have by the end of the month? What is the total amount? Again, if we use a table, that'll help us to work out what's going on, and we'll be able to find the pattern, if there is one. So on day 1, he receives $1 and the total is 1. On day 2, he receives 2 and the total is 3. Day 3, he receives 4 and the total is 7. Day 4, he receives 8 and the total is 15. Day 5, he receives 16 and the total is 31. On day 6, he receives 32 and the total is 63. So what is the pattern here? Well, since we're doubling something, think of the powers of 2. I look at this and I want to find if there's a relationship between the number of days and any of these numbers. Well, the first thing I see is that, say day 4, well, that happens to be 2 cubed. And that on the 5th day, it's 2 to the 4th power. And on the 6th day, it's 2 to the 5th power. There's a pattern. Now this number, I look at that 4, it happens to be 2 to the 4th power minus 1. And here, 31 is 2 to the 5th power minus 1. And 63 is 2 to the 6th power minus 1. Now I want to know the total amount. So here is the pattern. It's 2 to the number of days minus 1. So on day 30, the man would receive 2 to the 29th power, and his total amount would be 2 to the 30th power minus 1. If it extended to 64 days, then he would receive on day 64 2 to the 63rd power, and his total amount would be 2 to the 64th power minus 1. I mention the 64th day because this relates to the original problem, which was a chessboard, and square 64 would be there. And there's an ancient story that a wealthy ruler once asked a wise man what he would like for a reward. He said he would like 1 grain of wheat or rice on day 1, 2 on day 2, 4 on day 3, 8 on day 4, and so on till the whole chessboard was full. It is said that the ruler agreed to this reward, but by the 64th day there was not enough grain in the whole kingdom to pay the wise man. We can divide the chessboard into two halves here. This is the first half of the chessboard and this is the second half. Now, when you have exponential growth, the growth in the second half is billions of times more than in the first half. And this has given rise to the expression, the second half of the chessboard. And I'll explain this now on the whiteboard. We know from our worksheet that the total amount at square 32 would be 2 to the 32nd power minus 1. And on the 64th square, the last square of the chessboard, it would be 2 to the 64th power minus 1. I'd like to ask the question, how much larger is that number than this number? Well, if I round these numbers to 2 to the 64th power over 2 to the 32nd power, we know by the second law of indices that the answer here is 2 to the 32nd power. 2 to the 32nd power minus 1 is in fact 4,294,967,295. It's over 4 billion. Now 4 billion has 9 zeros. So if I multiply 4 billion times 4 billion, I get 16 followed by 18 zeros. And that's a quintillion. 2 to the 64th power minus 1 is in fact 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,615. But I find it easier to think of it this way, that by the time you get to square 32, that is the first half of the chessboard, the total is over 4 billion. But by the time you get to the 64th square, the end of the second half of the chessboard, it's a billion billion. It's about 18.5 quintillion. The result of exponential growth. A good modern example of exponential growth is Moore's law. In 1965, Gordon Moore of Intel predicted that transistors in a dense integrated circuit would double every year for the next 10. It turned out to be true, and for subsequent decades, Moore's law, as it became known, was true for every period of about 18 months. Since 2013, that's 32 by 1.5 years, 48 years since 1965, we have entered the second half of the chessboard for Moore's law. Does Moore's law still hold true? Well, according to Intel, it still does for every period of 2 to 2.5 years. If you're interested in Moore's law, there's plenty about it on the internet.